In the last module, we have developed formal definition of polynomials and discussed algebraic structure of the polynomial rings. In this module, we will develop division algorithm of polynomials over a commutative ring with unity. In the ring Z of all integers, we have a fundamental result known as division algorithm. This demonstrates how to divide any integer by a non-zero given integer. Also, we know division of polynomials with real coefficients. Target of this module is to develop an analogous result in the ring Rx of all polynomials over a commutative ring with unity. Recall that though we call division algorithm for integers, still it is not at all an algorithm. It just asserts existence of quotient and remainder. Here also we see that the analogous result which we call division algorithm for polynomials also asserts existence of two polynomials which we will call quotient and remainder, but it does not give any formal procedure how to find quotient and remainder. Before going into the details of division algorithm, let us first introduce the notion of divisibility in the polynomial ring. Suppose R is a commutative ring with 1 and f x, g x are two non-zero polynomials in R x. If there exists a polynomial q x over R which satisfies f x equal to q x into g x, then we say that g x divides f x. Equivalently, we also say that g x is a factor of f x. It is denoted by this symbol which we read as g x divides f x. Now, the most important fact here to notice is that if we want to divide a polynomial f x by some non-zero polynomial g x, then we have to assume that the leading coefficient of g x is a unit. To explain this, let us consider two polynomials g x and f x over Z, that is the over ring of all integers. Suppose g x is 2x plus 1 and f x is 3x square plus something. So, if we want to divide f x by g x, then our problem is to find some integer n, so that 2n equal to 3, but it is never possible over Z. That is why we need to assume that the leading coefficient of g must be a unit, so that it can divide every element of R and we can perform division algorithm for dividing any polynomial f x by g x. Thus, the formal statement becomes that if f x and g x are two polynomials with leading coefficient of g x a unit in R, then division algorithm states that there exist unique polynomials q x and r x over R such that fx equal to qx into gx plus rx, where either rx is the zero polynomial, and if rx is non-zero, then the degree of rx must be less than degree of gx. Probably this is the fact why this result is known as division algorithm, particularly known as algorithm, because this restriction determines that, asserts that the division process will terminate after finitely many steps. Anyway, to prove this, we will use induction, and this result has two parts. One is existence and the other is uniqueness. First, we prove existence of qx and rx. Note that gx is a non-zero polynomial. So, if gx divides fx, then there exists qx in rx such that fx equal to gx into qx. In this case, if we consider rx equal to 0, then the required presentation is obtained, and if gx is not a factor of fx, then consider the set S equal to fx minus qx into gx, where qx runs over rx. Actually, here we use the equivalent form of the induction principle, which is known as well ordering principle of the set of all non-negative integers. Here we apply the well ordering principle on the set n of all possible degrees of hx, where hx is an arbitrary member of the newly constructed set S. Since this is a set of degrees of some polynomials, first we should note that in S there is not the zero polynomial. Since we have assumed gx is not divisible, fx is not divisible by gx, so S does not contain the zero polynomial, and hence there is no problem to get n. By the well ordering principle, we have the least element of n, which will correspond some polynomial of S. Suppose Rx belongs to S, is a polynomial of least degree among all the polynomials in S. Then there exists Qx in Rx such that fx equal to gx qx plus Rx. So, we get two polynomials qx and Rx which satisfies the identity fx equal to gx into qx plus Rx, but still it remains to show that Rx satisfies all desired condition, that is either Rx is zero polynomial, or if it is non-zero, then degree of Rx is less than degree of gx. Since we have assumed that gx does not divide fx, so Rx can never be 0. So, here we are to show that degree of Rx becomes strictly smaller than degree of gx. Assume that gx is a polynomial of degree n having coefficients ai, and Rx be a polynomial of degree m having coefficients bi. We have already assumed that gx is a polynomial having leading coefficient unit. So, an is a unit and an inverse exists in R. Suppose on the contrary, let us assume that degree of Rx is not less than degree of gx. Then degree of Rx becomes greater than equal to degree of gx, and in this situation we construct a new polynomial fx equal to Rx minus bm into an inverse into x to the power m minus n into gx. The motivation behind constructing Sx in such a way that the degree of Sx becomes less than degree of Rx. That is why we subtract a term Bm an inverse x to the power m minus n into Gx from Rx, so that the leading term of Rx, that is Bm x to the power m, vanishes. Then Sx is a non-zero polynomial. If not, then Rx becomes equal to Bm into an inverse into x to the power m minus n into Gx, and we get Fx is a multiple of Gx. Equivalently, Gx divides Fx, but we have already assumed that Gx does not divide Fx. So, Sx is a non-zero polynomial, and Sx equal to Fx minus Qx plus Bm an inverse x to the power m minus n into Gx shows that Sx has the form, prescribed form of the elements of S, that is Fx plus something multiple of Gx. Also we have degree Sx is less than degree Rx, which contradicts the choice of Rx in S as a polynomial of least degree. Therefore, degree of Rx must be less than degree of Gx. Now, we are to prove the uniqueness of Qx and Rx. Assume that there are also polynomials, say Q dash x and R dash x, such that Fx equal to Q dash x Gx plus R dash x, and R dash x satisfies the desired conditions. Then Qx into Gx plus Rx equal to Q dash x Gx plus R dash x implies that Rx minus R dash x equal to Q dash x minus Qx into Gx. If Rx minus R dash x is non-zero, then Q dash x minus Qx is also non-zero. But since the leading coefficient of Gx is unit, then the degree of Q dash x minus Qx and Gx becomes the sum of their individual degrees, which becomes greater than equal to degree of Gx. Thus we get degree of Rx minus R dash x becomes greater than or equal to degree of Gx. But since Rx and R dash x both are of degree smaller than the degree of Gx, it is never possible. So, our hypothesis that Rx minus R dash x is not equal to 0 is wrong, and it follows that Rx equal to R dash x, which again implies that 0 equal to Q dash x minus Qx into Gx, which implies that Q dash x minus Qx equal to 0. Note that here we have not used the properties that the ring Rx has no divisors of 0. This follows only because of the fact that the leading coefficient of Gx is a unit. Thus we get Rx equal to R dash x and Q dash x becomes Qx, and hence both existence and uniqueness follows. In this theorem, we get Qx and Rx as unique polynomials which satisfies some prescribed conditions. This uniqueness induces the definition of quotient and remainder when we divide some polynomial Fx by a non-zero polynomial Gx having unit leading coefficient. We will say that if Fx and Gx are two polynomials which satisfies Fx equal to Qx Gx plus Rx, where either Rx is a zero polynomial or degree Rx is less than degree Gx, then we say that Qx is the quotient and Rx is the remainder when we divide Fx by Gx. Thus, we get an analog of the division algorithm in the ring of all polynomials. And there are several consequences of such a powerful result. Among these consequences, the most important is the factorization theorem and another is remainder theorem. This remainder theorem and factorization theorem actually tells about the root of a polynomial. As we have seen earlier, it may be that a polynomial f x, if it is considered over a ring R, then it may be that it has no root in R. Here we do not want to discuss about all possible roots of a polynomial, maybe in R, maybe outside R. Here our attention is on the elements of R which are roots of some polynomials over R. To define root of a polynomial, first note that if f x is a polynomial over R, then f x induces a function, a mapping from R to R. Given any a belongs to R, it corresponds to the value a0 plus a1a plus an a to the power n in R. We say that a belongs to R is a root or 0 of f x if f a equal to 0. Later we see that a is a root of f x if and only if the linear monic polynomial x minus a is a factor of f x. From this fact, we have introduced the notion of multiplicity of a root R. A root R is said to be of multiplicity m if x minus r whole to the power m is a factor of f x, but x minus r whole to the power m plus 1 is not, that is r is not a root of g x. And in this way we define root of a polynomial and multiplicity of a root. This theorem is known as remainder theorem, which states about the remainder when a given polynomial f x is divided by x minus a. Very interesting is that the remainder is obtained by a only. If R is a commutative ring with unity and f x is a non-zero polynomial over R, then for any a belongs to R, we have unique q x in R x such that f x equal to x minus a q x plus f a. To prove this, denote the polynomial x minus a by g x. Note that the leading coefficient of g x is 1 and hence a unit in R. So, the division algorithm can be applied to divide f x by g x, and we will get two unique polynomials q x and r x in R such that f x equal to x minus a into q x plus r x, where either r x equal to 0 or degree of r x is less than degree of gx. Note that degree of gx is 1. So, either Rx equal to 0 or Rx is a non-zero constant term. So, in either case we can assume that Rx is b, it may be 0, may be non-zero, and hence we get Fx equal to x minus a into Qx plus b. Since b is independent of x, we get Fa equal to 0 plus b, that is Fa equal to b. Replacing b by Fa, we get Fx equal to x minus a into Qx plus Fa. Here again we wish to recall that the result states only about the remainder when a polynomial Fx is divided by a particular form of polynomial, namely x minus a. Now, we prove factorization theorem. To characterize polynomials Fx divisible by x minus a, there is a very close relation between such divisibility and a being a root of Fx. Actually, x minus a divides Fx if and only if a is a root of Fx. Thus, we see that the natural consequences of division algorithm like factor theorem and remainder theorem holds for the polynomials over commutative ring with 1. Now, we show that there are other consequences which is not similar to the polynomials over the field of real numbers. I am talking about the number of roots of a polynomial. We know that if Fx is a polynomial of degree n over the field of real numbers, then it cannot have more than n roots, either real or complex. Now, we show that there are commutative rings and polynomials over commutative rings such that a polynomial of degree even 1 may have more than 1 roots. Suppose consider the ring Z12 of all integers modulo 12 and consider a polynomial 3x of degree 1. Then note that 4 and 8 are 2 roots of this polynomial. Thus, we have a polynomial of degree 1, still it has 2 roots. Actually, this happens because the ring Z12 contains divisors of 0. We show that if a ring R does not contain any 0 divisor, then the bound on the number of roots can be imposed like the polynomials over the field of real numbers. Suppose Fx is a non-zero polynomial over an integral domain R and degree of Fx is n. We show that Fx has at most n roots in R and it is counted according to multiplicity. We prove this result by the method of induction on degree Fx. For the basis step, assume that n equal to 0, then Fx becomes a non-zero constant in R and hence has no roots. And let us make our induction hypothesis that the result holds for all non-zero polynomials f x having degree less than n, and consider a polynomial f x, a non-zero polynomial f x of degree n which is greater than 1. If f x has no roots in R, then the result holds. Suppose f x has a root, say a belongs to R, then f x becomes x minus a into some polynomial f x, which follows from the factorization theorem. And since R is an integral domain, here the degree of product is equal to sum of the degrees, and from which it follows that degree of the polynomial f1x is n minus 1. Then by the induction hypothesis, f1x has at most n minus 1 roots in R. Now we show that if b is a root of f x in R and b is not equal to a, then b is also a root of f1b, which will prove precisely that every root of f1x in R is also a root of f x. Then fb equal to b minus a into f1b. Since we have assumed b is not equal to a, so b minus a is non-zero, and since R is an integral domain, so b minus a into f1b equal to 0 implies that f1b must be 0. Equivalently, b must be a root of f1x, and hence it follows that f x can have at most n roots in R. Using this result, we have a fantastic characterization on the equality of polynomials. Recall that two polynomials f x and g x are equal if either they both 0, and if they both are non-zero, then their degree is the same with their corresponding coefficients equal. So, if f x is a polynomial of degree n with coefficients a I, and g x is a polynomial of degree n with coefficients b I, then the condition for equality of f x and g x is that a I is equal to b I for all I. Here we give an equivalent, rather alternative characterization for f x and g x to be equal in terms of roots. Here we show that if R is an integral domain and f x, g x, two polynomials such that their degree does not exceed n, and f a equal to g a for n plus 1 elements, then the polynomials f x and g x will be equal. We will prove this result by the reductio ad absurdum, which we know as by the contradiction method. So, assume on the contrary that f x and g x are not same polynomial, then h x equal to f x minus g x becomes a non-zero polynomial over R, and since degree of h x is less than equal to n, if we can show that h x has at least n plus 1 roots, the conclusion will contradict the previous result. Note that fx and gx becomes equal at n plus 1 values a in R. So, all these values will be a root of hx, and hence hx becomes a polynomial of degree less than equal to n, but has at least n plus 1 roots in R. This contradiction asserts that fx must be equal to gx. Thus, in this module we have characterized relation between roots and factors and deduced the division algorithm. There are many other consequences of the divisibility of polynomials, especially of the polynomials over a field, such as greatest common divisor of polynomials and irreducibility of polynomials. These two are very important ideas in polynomials. Like prime numbers, the irreducible polynomials will form basic building blocks of the polynomials, which we will discuss in the next module.